Welcome back to Hands-on FPGA Design, from theory to implementation. I'm Albert. Today, we are moving on to Lab 6, building an SoC system with custom AXI slave master interfaces in VRAM and Vivado. In our previous labs, we mastered how to construct a basic SoC platform and utilize slave interfaces for CPU-controlled hardware peripherals. Today, we are taking the challenge to the next level. Our primary focus is learning how to utilize master interfaces and integrate VRAM storage spaces. This is not only the core of high-performance hardware acceleration, but also the absolute foundation for handling massive data transfers. Let's do a quick recap of our course progress. Up to this point, we have already learned how to let the CPU actively communicate with our hardware peripherals. In today's lesson, however, we are going to introduce the master interface along with VRAM. This will grant our hardware circuitry the capability of autonomous memory access, which is an absolute must-have technology when dealing with high-performance data transfers. Here is the outline for today's session. Before we begin, please ensure that you are fully prepared. For detailed content, please refer to the pre-lab course. There are 3 core objectives for this lab. First, to get familiar with the AXI full bus protocol. Second, to learn how to package and design a master interface circuit. And finally, to understand the operational mechanism of VRAM. This time, we will implement an arithmetic logic unit, ALU, that can utilize its master interface to actively read multiple sets of operand values from the VRAM, execute the computations, and write the results back, including their respective storage addresses. As shown in the diagram on the right, we will process 16 separate operations in a single batch, displaying the 2 input values, the operational mode, the target storage address, and the execution results right inside the terminal. Next, let's get to know AXI Full. Unlike the AXI Lite interface we used in our previous lab, AXI Full supports a highly powerful feature called burst mode transmission. In AXI Lite, every single data transfer requires an individual handshake from scratch. AXI Full, however, allows us to provide just one single starting address, and then continuously transfer up to 256 data payloads in a single burst. This design dramatically improves our bus bandwidth efficiency, which is exactly why we must rely on AXI Full when handling high-resolution video streams or complex high-performance computations. Below on the slide, you can see the write and read channels for AXI Full, which share the exact same structural layout as the AXI Lite channels we introduced last time. Next, let's introduce VRAM, or block RAM. It is a dedicated memory resource embedded inside the FPGA fabric, characterized by its high bandwidth, low latency, and native support for AXI Full burst mode transmissions, making it ideal for processing multiple data streams. For this lab, we partitioned the VRAM into 2 distinct regions, an input region and an output region. When the master interface initiates a read request, data flows directly from ALU_in into our ALU. Once the computation is complete, the master initiates a write request to store the results back into ALU_out. This architectural layout ensures that data flows entirely within the local hardware without the need to constantly loop back to the primary system memory, thereby achieving exceptionally low latency. Next, let's examine our experimental circuit. To start off, the CPU utilizes the AXI bus to write the target computational data into the VRAM. Then, by performing a write operation to the slave interface, the CPU triggers the slave to control the master's actions. Upon receiving this command, the master actively initiates an AXI transaction to read the data from the VRAM and feeds it directly into the ALU core for computation. Once the ALU completes the execution, the master writes the final results back into the VRAM. Finally, the CPU accesses the VRAM to read out the calculated results, completing the entire closed-loop workflow. You can refer to the actual system block design right here in the bottom right diagram. Now, let's lock our focus onto the internal architecture of both the slave and master interfaces. First, look at the slave interface on the left. Its primary task is to serve as the communication gateway for the entire hardware system. When control commands come in, the slave interface is responsible for receiving and buffering critical parameters. First is the start signal, which acts as the master switch to trigger the hardware execution. Second is the number of ALU calculation sets, which determines exactly how much data the master will need to transfer down the line. Additionally, the slave is also responsible for returning the done status signal. Next, let's look at the master interface on the right. The moment it receives the trigger signal routed from the slave side, it actively initiates address requests. Based on the preset base addresses, the master autonomously accesses the BRAM controller, fetches the operands, and feeds them directly into the ALU for subsequent computation. This slide displays our address mapping table. Within this configuration, you'll notice that one of the slave's internal registers is actually left unused or reserved for future scaling. Similar to our previous lab, the workflow for this experiment is divided into three main sections. First, we have the ALU block. Next is the PL side, and finally, the PS side. You can download the required source code examples for this course from the link provided.
Let's start our project now. First, launch Vivado and click on Create Project. Name the project lab6_ALU. Select RTL project, check the box for Do Not Specify Sources, and choose the ZedBoard as our target device. Next, click Add Sources. Select Add or Create Design Sources. Click Create File and name it lab6_ALU. Double-click to open the newly generated source file and copy and paste our sample ALU Verilog code right inside. Following the same steps, click Add Sources again. Choose Add or Create Constraints. Click Create File and name it lab6_ALU. Open the file and paste our sample constraints template. Next, click Run Synthesis on the left menu. Once completed, simply click Cancel on the pop-up window. Go to the top menu, click Tools, and select Create and Package New IP. Choose Package your current project. Switch to the Review and Package tab, and click the Package IP button to finish packaging our custom ALU core. Now, close Vivado. Relaunch Vivado. Click Create Project. And name this project lab6_example. Keep all settings the same and select the ZedBoard. Go to the top menu, click Tools, and select Create and Package New IP. Choose Create a new AXI4 peripheral. And enter lab6_slave_master for the name. Since this IP incorporates both slave and master interfaces, we need to click the plus sign to add a new interface. Rename the new interface to M00_AXI change its type to Full, and set its mode to Master. Select Edit IP to launch a temporary editing workspace. In this workspace, we need to modify 3 source files. Simply copy and paste the corresponding sample codes into each file. Once modified, click Edit Packaged IP in the top banner. Switch to Customization Parameters and click Merge Changes. Finally, navigate to Review and Package. Click Repackage IP and select Yes to close the editing workspace. Now back in our main project, click Settings on the left panel. Navigate to the IP directory under Repository. Click the plus sign and add our custom lab6_ALU IP. Next, click Create Block Design. To open the IP diagram workspace, first, click the plus sign to instantiate the processor core. And then click Run Block Automation to automatically connect fixed_IO and DDR. Click the Refresh button on the toolbar to clean up the routing layout. Now double-click the Zinc processor block to enter its configuration window. In the Peripheral Pins tab, disable all peripheral pins except for UART1. Then switch to PSPL configuration. And check the boxes for MAXIGP0 and SAXIHP0. Click OK and hit the refresh button again to update the layout. Next, click the plus sign to instantiate our custom lab 6_slave_master IP and click Run Connection Automation. Check the required boxes, click OK, and refresh the diagram layout. Now we need to instantiate 2 instances of the AXIB RAM controller. Double-click each controller block and change its B-RAM interfaces setting to 1. Next, instantiate a block memory generator. Double-click it and set its memory type to True Dual Port. Click OK. Now, click Run Connection Automation and check the All Automation box. Pay attention to the second SAXI interface selection here. Make sure to modify its target interface as shown. Once configured, hit the refresh button one more time. Next, instantiate our custom ALU IP block. We will manually make the connections between the ALU and our custom interface ports. Please follow the exact wiring connections displayed on the screen. Once completed, click the refresh button and your block layout should look like this. Finally, click the checkmark icon on the top toolbar to run Validate Design. Then right-click on Design 1 in the Sources window and select Create HDL Wrapper. Now double-click the Zinc processor block once more. Navigate to Clock Configuration, expand PL Fabric Clocks, and change the frequency of clock 0 to 25 MHz. Click OK. Then click Run Synthesis on the left menu. And hit Cancel when the pop-up appears. Just like in our previous lab, we need to remove the internal constraint file that causes clock conflict misinterpretations in Vivado. Right-click on our ALU IP block and select Edit in IP Packager. Locate lab 6_ALU.xdc under the Constraints directory. Right-click it and select Remove File from Project. Switch over to File Groups. Click Merge Changes. And finally click Repackage IP. Back in the main workspace, click Report IP Status from the top menu. Select Upgrade Selected at the bottom panel and then click Rerun to apply the changes. Now click Generate Bitstream on the left menu. Once completed, open the Hardware Manager. Go to the top menu and click File. Navigate to Export. Select Export Hardware. And check Include Bitstream. Next, click Tools on the top and select Launch Vitis IDE. Confirm your workspace directory and click Launch. Click Create Application Project. Switch to the XSA tab. And select the XSA platform file we just exported. Name our application project Lab6_test. Expand the SRC folder on the left, open helloworld.c. and overwrite it with our sample code. Just as before, we must manually modify the three makefiles as indicated on the slide so that the libraries link properly. Once all 3 makefiles are updated, select our hardware platform on the left Explorer tree and click the hammer icon to build it. Then, select the application project down below and click the hammer icon again to compile our C code. Once you've entered the workspace, please follow the diagram to connect the ZedBoard using cables and turn on the physical power switch. At this moment, the green power LED will light up. Next, go to the top menu, click Window, select Show View, and open Terminal. Click Open a new terminal at the bottom right. Select Serial Terminal and map it to your active COM port with a baud rate of 115,200. Finally, right-click on our application project, navigate to Run, and select Launch Hardware to execute the program. Upon successful execution, you can maximize the terminal window to view the output results. Right here, the terminal displays the initial state of the BRAM, followed by our 16 computational transactions. Each entry includes 2 operand values: the operational mode, the target memory address, and the final calculated result. Notice that our first value A is the square of the second value B, which directly matches the arithmetic logic we coded inside helloworld.c. The mode indicators 0, 1, 2, and 3 correspond to addition, subtraction, multiplication, and division, respectively. You can also verify the exact base address where each data entry is stored and double-check the mathematical correctness of each output. This concludes the hands-on section for Lab 6. Here is the demonstration of results for Lab 6. Looking ahead to our next lesson, the primary goal of Lab 7 is to build a lean, efficient verification environment. You will learn how to test our custom master wrapper directly via a test bench without depending on the Zinc processor core. We will utilize an AXI connector along with a BRAM controller to construct a standalone test bench platform, implementing an automated test cycle that encompasses write, read, and data comparison operations. The master wrapper will initiate a write request to store data, read it back from the exact same address, and perform an automated data integrity check. This allows us to rigorously verify our master logic and address mapping. I'm Albert. Thanks for watching, and I'll see you in the next class.